So my presentation is from muscles to brain motor unit based EEG filters. And because of schedule was a little bit messed up, this processing pipeline was already supposed to be presented, but I'll just do a quick overview of it. So processing pipeline consists of 5 segments. And in the first segment, we have high density EMG acquisition, which Matej already presented very well. In the second segment, we have identity EMG channel selection, where we are supposed to select channels in an optimal way so we will get more accurate results. And in segment C, we have blind source separation based motor unit filter estimation. And in segment D, we have motor unit filter optimization and power simulation. And those 2 segments are segments that I will present more precisely today. So if we start with the convolutive model of high-density EMG. So we have sources, and sources are actually motor unit spike trains. And from those sources, we have mixing coefficients or convolutive kernels, which are actually motor unit action potentials. And if we add all those motor unit action potentials together, and if we also add noise, we get the EMG, we get high-density EMG signals. And what the decompositional algorithm actually does, what it does is it reverses the process. So we start with the high-density EMG signals, and we are trying to get to sources, which are motor unit spike trains. And you can see that here mixing coefficient capture all the anatomic properties of skeletal muscles, while sources capture all neural codes or neural codes from the central nervous system. And for us to be able to do that, to extract the motor unit spike trains from the high-density EMG signals, we need a motor unit filter. And with the use of motor unit filter, we apply it to measurements, so to our high-density EMG signals. And as a result, we get spike trains as are visualized here. So here we have 5 examples, 4 examples of motor unit filters. And in the first example, we have Laplacian filter. And if we apply that Laplacian filter to the high-density EMG signals, we get this component, which is actually spike train right here. And with quality of that spike train, we are not really satisfied. There's still a lot of noise, and we can barely see anything in it. But if we now use 21 channels, we get this motor unit spike train, which is better. We are able to see some of the spikes, but we can also see a lot of contributions from other motor units, so we are still not satisfied with that result. And if we, instead of 21 channels, select 58 channels, or 28 and 51, I think, we get a better spike train, which is still a bit noisy, but it's very better in the accuracy. And now, at this point, we've used all the spatial coefficients of motor unit filter. And what can we add at this moment is delayed versions or delayed repetitions of every channel, which is visualized here. And if we add together spatial and temporal components for the motor unit filter, we get spike train as it's visualized here. And with that spike train, we are finally satisfied. During my presentation, I will talk a lot about the extension factor. And the extension factor is number of temporal coefficients, so number of delayed repetitions that we add to every channel. So how does everything look like in a matrix form? I have some of the matrix equations and some of the mathematics representation of the cumulative model, but I really try to simplify it, so I won't just kill you with math, don't worry. It will be very simplified. So we have a matrix H, and that matrix consists of motor unit action potential. And we can see that every column is a separate motor unit, and in every row, we have measurement from one electrode. And we will also have a vector T, and that vector consists of motor unit spike trains, as visualized here. Well, motor unit action potentials capture all anatomic and geometric properties from muscles. And here we can see an example of motor unit action potential by the muscle biceps brachii. And we can see that movements are actually present in nearly all the channels and that they are very similar in shape. On the other hand, if we take a look at the muscle follows, we can see that it's not that spatially supported and that it changes in shape more drastically. We may all know that biceps brachii is a fusiform muscle and soleus is pennated muscle, and we can see those properties are reflecting in the motor unit action potential shapes and spatial support. So the basic equation of convolutional kernel optimization, or the CKC method algorithm, is this one. We are multiplying matrix H with vector T. And here is a simple visual representation. If we multiply motor unit action potential with its spike train or pulse train, we get a motor unit action potential train. And if we add now all those together, we get high density EMG signal, which at this point is noiseless. For the rest of the presentation, I will just ignore noise, so everything will be more simplified. So for us to be able to fully understand the motor unit filter, we need to talk about the correlation matrices a bit more. We have two correlation matrices. One is the correlation matrix Y, and it's actually correlation matrix of measurements. And the other one is correlation matrix C, which is correlation matrix of pulse trains. Both of those matrices are symmetric, while this correlation matrix C is also diagonal if motor units are asynchronous. But if motor units firing more synchronized, then this is dominantly diagonal. And we can now express the correlation matrix of measurement with that basic equation that I showed you before. And we can see that we can express this correlation matrix Y with matrix H and correlation matrix of pulse train. This is important because this exact representation of correlation matrix Y we will later use on the motor unit filter. And we can see some visual representations of correlation matrix Y, so of its measurements, and you can see that those metrics are truly symmetric. And here we still have all the anatomic and skeletal properties of muscles. And for the correlation matrix C, we can see that it's diagonal, as visualized here. And here we don't have any anatomic properties anymore. We just have neural types or how many spike trains it is in every motor unit in every row. So first approximation of the motor unit filter is calculated with this form. So we have transposed vector of measurement at exact time moments, so that time moment at that moment will be n0, and we multiplied with the inverse of the correlation matrix Y. And if we now use that motor unit filter and apply it to measurements, we get this as a result. But if motor units are asynchronous, we can leave this inverse of correlation matrix T out, because we know that this correlation would then be diagonal, and also its inverse is diagonal, so we can just leave it out and we end up with this equation here. And how does that work in practice? So here, vector T at the time moment n0 has one active spike at that moment. And then the vector Tn is going through all its spike trains, and it is searching for that exact moment and where is if there is any motor unit active. And we can see that there is, and so that selector will enable to pick this first pulse train. But that works only if motor units are not firing at the exact same time, which we all know that this is not the case, not only in pathology cases, but even with healthy individuals. If you now think of how you act when you're lifting something heavy and you can just hold it anymore, then you start to shake. And that shaking is actually motor unit synchronization. And if more than one motor unit is active at the same time moment, we need to be aware of this onion principle. I was trying to visualize an onion here. Because the convolution of relativization is biased when it comes to the amplitude of spike trains of motor units that are active at the same time. So the recruitment order is at first smaller motor units will be recruited and then the bigger ones. And those smaller motor units will have a bigger firing rate than the bigger ones. And because of that reason, we'll get spike trains that are very different in amplitude. So then we need to do the optimal motor unit filter, and we do it with the cross-correlation coefficient between pulse train at index I and all the pulse train. And here we have a vector. And for us to be able to do that calculation of the cross-correlation coefficient, we need to know the pulse train at the end at the index I. And that is only possible if we estimate motor unit filter iteratively. So at that moment, we are here, we already did the initialization of motor unit filter, and now we are calculating the motor unit spike train optimization. Now we are in optimization of motor unit filter, and then we are in this optimization loop. So we need to estimate motor unit filter iteratively, just because we need to know the estimation of the spike train at index I. And this iterative optimization of motor unit filter we have in segment D. So now we moved on to segment D. And this segment or this process is at our university performed manually with the use of the DEMUSE tool. For those who are not familiar with that, the DEMUSE tool, this is a software that was developed by our university, and it enables us to decompose signals with many different parameters. It also allows us to plot signals in many different ways, to use many different filters, and for us, the most importantly, we get to manually edit the decomposition results with the use of the CKC inspector. If we take a look at the CKC inspector, we can see that at the top, we have the pulse to noise ratio, and we can select motor units that were decomposed with this algorithm. And in the upper panel, we have motor unit action potentials that were identified in channels. In the middle panel, we have instantaneous firing rate, and that gray line represents force. So here was the symmetric contraction, and that lower panel consists of motor unit spike train, which is visualized with blue line section, and we can see those red circles, which are denoting firings that belong to that exact motor unit. And what we actually do while we manually edit the composition results, we are actually selecting and deselecting those red circles, and we are applying the motor unit filter. The first thing that we usually do when we are manually adding the composition results is the outlier removal. And we can spot the outliers by having a bigger change of amplitude or having a bigger change of instantaneous firing rate. So we can see that those firings clearly do not belong to that motor unit, and that's why we need to remove them. And when we remove them, we get the result that is visualized here. And maybe we can here also observe the pattern that has showed in the middle panel. We can see that motor unit slowly increase its instantaneous firing rate during the ramp up phase. It was nearly constant during the hold phase, and it also decreased during the ramp down phase. The opposite of duplicated or outliers are missing firings, and we can spot them by having those spike trends that are not selected, or by having instantaneous firing rate firings that are very that are more slow than the rest of them. And we resolve this by adding them. Okay, so when we do the outlier removal and when we are adding the missing spikes, we need to reapply the motor unit filter. So we have now did another estimation of motor unit filter, and we now need to reapply it to measurements. So we'll get a new spike train. And this is the result that we get after reapplication of that motor unit filter. Merged motor units are sometimes very similar in shapes. And for that reason, the transition algorithm identifies them as merged motor units, as we can see here. Here, this is one motor unit that already has accurately identified firing. And here, lower, we have another motor unit. And we need to resolve that issue by subtracting them into two separate motor units. Let me just acknowledge that there can be more than two motor units that are merged in just one. So I think that example we only have two. And we resolve this into motor unit 1 and motor unit 2. At the end, we usually need to delete motor units. I mean, not usually, we always need to delete motor units. And I really prefer those 5 rules because I think they allow you to be consistent, and it's kind of a cheat sheet that I have. So we need to delete a motor unit if its pulse noise ratio is lower than 24 decibels. And if we have at least 3 different heights of amplitude in the pulse rate. If we also do not recognize any clear ramp up, hold, or ramp down patterns in the middle, instantaneous firing rate pattern, that motor unit also should be deleted. And if a motor unit has less than 10 firings, it should be deleted. And here we have some examples. So here we have a motor unit with a pulse to noise ratio which is lower than 24 decibels. And you can see that pulse to noise ratio is actually having this short because that motor unit is really poorly recognized. The accuracy of the identification is catastrophic, and we don't even have any clear pattern in the instantaneous firing ratio. This is another motor unit should be deleted. Not only that it doesn't have a regular firing pattern, it also doesn't have a regular, semi-similar amplitudes in pulse range. It also has very weird motor unit action potential shapes. And here is also another example of motor unit that should be deleted. We don't have a pattern of ramp up, hold, or ramp down phase, and also spike heights are very different. Okay, so now we actually know everything that is required for us to know, so we can move on to EEG signals. So we know that if we estimate a motor unit filter and if we apply it to EEG signals, we get a motor unit spike train. But what do we need to change so that similar method would be applicable to EEG signals? Changes are very small. So instead of EMG signals, we now have EEG signals, and instead of spike train at I, we have a cumulative spike train. And as a result, we now get a EEG component, which consists of different sine waves. I could say it like that. So in theory, there was one study made using that proposed approach. And in this study, an experiment was made, and it was based on a consumption that cumulative spike train in the tremoric muscle have same properties as the tremoric EEG component. So we know that the cumulative spike train and cortical tremor component are coupled via some unknown function, and we are trying to exploit this. So we are trying, with the use of cumulative spike train, to extract those cortical tremor components, and the other EEG sources are non-tremoric components, and now mixing coefficients. Before they were measuring action potentials, but now there are some other brain activities. And for the rest of this model may seem familiar because it's the same as it was in previous case. So in this experiment, in this study, at first everything was tested on simulation signals, on simulated signals, and in those simulated signals, actually oscillators that look like EEG signals were generated using a mixture of sine waves. And with the B, we are denoting a basic frequency of tremor. And with H1, we are denoting the first harmonic of that frequency. And we can see that if we test those results, I mean, if we look at those results here, we can see that with parameters of signal to noise ratio of 10 decibels, and with the standard deviation of firing time delay was 10%, and the relative power of the first tremoric high harmonic was set to this value, and extension factor was set to 10. And with those results, we are able to see that the estimated, so those blue line, EEG component is very similar to the actual simulated one. So this is exactly what we want to get. And at this point, we have asked ourselves, what is the optimal extension factor? And we have tried out different extension factors, and we have calculated the cross correlation coefficient, the normalized mean square error between the estimated tremoric component and the simulated one, and we also visualize the relative power of the first tremoric harmonic. Please say that fast 3 times. It's very hard. And we can see that the optimal extension factor here was at 3 or higher. And those blue lines actually represent the average values, while dashed black lines represent standard deviation. And here, dashed red line is the actual value of the relative power of the first tremoric harmonic. And here we can see similar results with different parameters, only now the optimal extension factor was at 8. Also, that method was later tested on the real experimental signals. And here, 9 people with attention tremor and 9 people with Parkinson's disease performed the experiment. It was a postural task of holding a wrist completely calm. And in the first plot here, we have an acceleration plotted. And here we have wrist extender and wrist flexor plot. And that thick red line represents a cumulative spike train of wrist extenders, and thick blue line represents a cumulative spike train of wrist flexors. That spike train, I mean, that blue line is inverted just for the visual reasons. So I think this figure. And every square here represents a motor unit firing, and every row is a separate motor unit. Here in the segment C, we can see the cumulative power of the extensors, wrist extensors with the red line, wrist flexors with blue line, and the black line represents the acceleration on the wrist. We can see that the basic tremoric frequency yielded in both cases, while the first harmonic was visible only in cumulative spike rate. And then we have investigated how was cumulative spike train of extensions and flexures synchronized with the EEG component that we extracted using the proposed method. And here is the representation in time, and here is in frequency domain. And in frequency domain, you can see that there is a clear similarity of the basic tremoric component of the basic frequency of tremor, and also its harmonics in both cases, and also in acceleration. And lastly, in this study, it was investigated how this method performs compared to the other more standard method, and that usually use spatial filtering. So we can see that signals are now separated in channels, and the coherence was calculated, but there was no significant incoherence in separate channels. But if we now calculate coherence between our extracted each component, we can see a significant result. So this is evidence that proposed method outperforms classical standard method. And lastly, in this research, a burst tomography was done. You can see people, I think you recognize this model. It was made with the use of Fluorepa. And with those EMG signals that were acquired on the tremoric muscle, surface EMG decomposition was done, so we got out spike frames, and then that motor unit filter, which was made with cumulative spike frame, was applied to multi-channel EEG signals. So we got those phase log EEG averages that we can then see on this range model. And we can then clearly see source of the tremor. That would be it for my presentation.